So I think we're all familiar today with LLMs, and most people use some form of AI now on their phone. But Rich talked about the era of experience, which is going to be where AI is going next. And we find today that getting AI to work on physical robots is extremely difficult. And I know because I've tried to do this for over 12 years now, it's really, really hard. It struggles to generalize, and it can't deal with edge cases and complex environments. So we can take something like a general purpose humanoid robot and give it a single task to do that it can learn to do from a lot of training data. But if we take that same robot and we now put it in a general environment that's complex or dynamic or changing, it tends to fail a lot. And this is a problem that really hasn't been solved at all yet. So the main question to ask is, how is the human mind different from embodied AI today? We are conscious. Consciousness is really interesting to me, because we all have it and we all know it very intimately. Yet science doesn't really know what it is or how it works. And we also are now developing AI systems that are smarter and smarter. We also have no idea whether they are conscious. And I just think this is a really interesting state of affairs that we're in at the moment. We're building systems and we don't even know whether they're having any experience at all or what experience is. So I want to dive a little bit into consciousness today, giving you some examples. Hopefully everyone will be able to follow along and think about our own consciousness. So if you think about the way the mind works, we have two main modes of operation in our everyday life. The first is autonomous decision-making, and the second is conscious decision-making. So let me try and explain these two modes with an analogy that hopefully everyone should be familiar with, which is driving. So most people learn to drive at quite a young age, and after you've been driving for many, many, many years, it becomes this sort of autonomous activity. People actually report, as Jay mentioned, not being able to remember how they got to work that day because they weren't paying attention or being aware of driving at all. It was a completely autonomous activity, and you're often thinking about something completely different while you're driving. But if something unexpected happens while you're driving, like a vehicle suddenly swerves in front of you, your mind goes into a totally different mode. You suddenly become hyper-aware. You have a rush of emotion, adrenaline, feelings come online, instincts kick in. You go into a totally different mode of operation. And it's really interesting to compare these modes to each other and ask, what is going on? How are these two things so qualitatively different from each other? AI doesn't have these two modes. It only works in that first mode, the autonomous decision-making, once enough training examples have been seen that a task can become like a form of muscle memory. It doesn't have this ability to engage its consciousness and fall back on this system that gives us that instinctive ability to act when a situation has never been seen before or we're in an unfamiliar environment. So for AI to handle the real world, we need a new theory. So I'm exploring one such theory at the moment, and I'm exploring it from a scientific perspective, so that means it's not been verified. It's an open scientific question as to whether this theory is correct or not. And also there are many other theories of consciousness that need testing. But the reason I'm interested in the one I'm going to talk about today is because it's actually recently just become experimentally testable. So it's really cool. So that theory is called quantum consciousness theory. And this is the idea that there may be quantum effects going on inside our brain, and that these in some way may contribute to our consciousness. So in the quantum consciousness theory, these autonomous decisions, like the driving on autopilot example, are done using classical computation going on in the brain. But when we switch into that conscious, aware, instinctive mode, we're actually moving to a form of quantum computation in the brain. And I should reinforce, no pun intended, that all AI today works in the former category. We're really only just starting to test the waters of what quantum computing and quantum physics could give us for AI. So we're really in the bucket of a fully classical computation when we design AI today. Now, quantum consciousness sounds like a really kind of weird, new, wacky theory, but it's actually quite an old idea. Back when quantum mechanics was originally formulated in the 1920s, the early founding fathers of the field thought a lot about consciousness. They were actually very worried that somehow observers seemed to be affecting physical systems when they started looking at them. So there's been a link between quantum and consciousness for much longer than you might think. So let's just recap the difference between classical computing and quantum computing. I certainly don't have enough time to give you a full lesson of quantum computing and quantum physics, but I'll try my best to summarize it. So in a classical computation, you have information coming into your computer and information coming out of your computer, and it's generally represented as binary zeros or ones, and that computation is performed inside the computer using something called Boolean logic operations. So these are and, or, not gates that are used to manipulate these 0 or 1 symbols. Quantum computing is completely different. So the way quantum computers process information is not like that at all. There's this thing called the quantum wave function. So you can create a quantum wave function by, again, taking some classical information in and using that as the parameters to shape this weird thing. And you can get classical information out, but once it's in the quantum computer, it's a completely different kind of information. And there are properties it has that are very different than binary information, such as superposition, entanglement, interference, and coherence. So again, these are a bit too complicated to get into in a short time, but I picked this diagram for a very specific reason, because when I saw this picture, it kind of clicked for me. I was like, yeah, that's a really good visual metaphor for quantum information, because the zeros and ones, if you look closely, are still in there, but they've all been shaped, and now they're all moving together as one. And they've also taken on a new property of color. So a quantum system can be thought of as having zeros and ones inside it, but now those zeros and ones are taking on different qualities. In a quantum computer, you can have superposition where zeros and ones become a bit 0 and a bit 1 at the same time, so they become kind of fuzzy and mixed, and then they can be entangled, which means that the zeros and ones can actually know what each other are doing. So imagine if the transistors inside your desktop computer all knew what each other were doing in some weird telepathic way. That's a little odd, but we see that with quantum systems. And this wave shape overall gives me a sense of quantum information being more like a kind of analog, almost a living, breathing system, which, as we find out later, may be more than just a metaphor. There's one other thing that happens in quantum computing, which I really need to go into, because it's very important for what we're going to talk about next, and that's this concept of collapse. So I mentioned that the information is in this weird kind of quantum living, breathing state, but you can take a measurement of the quantum system, and when you do that, you get classical information out. So this weird quantum state with all these unusual properties turns back into classical zeros and ones when you read out the quantum computer. So in that way, the quantum computer has the same interface with the environment as a classical computer, zeros and ones in and out, but what's going on inside is very different. So the way we think of the human brain normally is that we have a body, as we've been talking about, previous speakers, a nervous system. We take perception information coming in through our senses. Something happens where the neurons compute somehow, and then action signals get sent back out from the brain to our muscles. So that's the kind of standard model of how it works. In the quantum consciousness model, there's actually two separate routes the information can take. One is this classical route, and the other one is now a quantum processing route. And the idea is that the neurons can use either of these two routes. So let's look at the classical one. In the case of classical computation, this mimics the autonomous mind switched off driving scenario we thought about earlier, where you're really not having any kind of experience at all. Just like there's nothing playing on the TV screen, you're not aware of anything. But in the quantum case, something very different happens. When you have this wave function coming online, this theory states that this is what causes us to have a first-person subjective experience of the world. So when the quantum processes come online, you actually start experiencing, you switch into conscious processing mode. And it's almost like something is now observing what's going on around you. And then the collapse is potentially even more interesting. So you're having this experience, and then this wave function collapses. What does that correspond to? Well, in the theory, this is what gives us a sense of agency or a sense of free will, making a decision. So in the driving mode, the decisions are being made completely autonomously for you, and you don't really know what's happening. But when you're conscious, you're very specifically choosing one action over another. So this is the quantum consciousness model of free will. Until recently, all this has been completely philosophical speculation, which, whilst interesting, is not so interesting to people like myself that want to actually build things and test things. But something happened recently that's been very important, and that is the rise and maturing of quantum computing technology. Quantum computers are here today, and they're getting better and better every year, and they have these properties built into them now: superposition, entanglement, collapse. They can do all that. So can quantum computers help us test these quantum consciousness hypotheses? Here's the idea. Imagine if we put a robot in a feedback loop with a quantum computer. We shape this internal quantum wave function with the perception data coming in from the robot, and we allow the action that that robot takes to be decided by the collapse of the wave function. This has never been done before. So this is a whole new area of research. We're really only just beginning, and to me, that's very exciting. So just going back to our human brain model, we have these two parallel processing paths, classical and quantum, theorized. But now we can actually build a synthetic analog of this system. We can have a robot with all the classical learning capabilities, but now we can add in an extra quantum computing route into its mind as well. Will it have a first-person experience of the world? This idea that when the quantum processing comes online, the observer turns on and there's something playing on the TV screen, that's what we're really interested in here. It probably won't be anything like a human experience, but it might be something like a proto-spark of experience, something like what an insect or an ant might experience. Will it have feelings? We have feelings and preferences and emotions, and these drive us to make our decisions. And most importantly, will it have agency? So we make different decisions when consciousness turns on. Perhaps the quantum system will too. So whilst we can't test for an inner subjective experience, we have no way of getting inside someone's mind and experiencing what they experience. What we can test for is, are the actions that a system selects different in the case of the classical computer being in control versus in the case of the quantum computer being in control. So here we have a scientific experiment we can actually perform where we switch from quantum to classical and back and forth, and we see, is this robot system or this AI agent choosing differently when we believe the consciousness is online? So let's just quickly dive into where this difference might come from, because it ties into Rich's stuff. In the classical system, the way we train AI, as Rich talked about, is we have a reward function. Reward signal. Sorry, he's correcting me on that one. The reward signal is either programmed in by a person or it's learned from mimicking human training data. But in the quantum system, if you remember, we had this collapse process happening, which we've tied to agency and free will. So the quantum system just chooses for itself which action to take. There's no reward function needed. There's no training data needed for systems like this. So this raises a really interesting question, which is, does life itself access some kind of built-in reward function that's deep inside physics we don't really understand a lot about yet? Could this be what causes us to have these instincts, these feelings, a will to live, and these sudden creative insights that seem to come out of nowhere that AI is having a very hard time modeling today? And I put a picture of some little single-celled organisms in the background, because if you watch these guys under a microscope, like I like to do for fun, they exhibit many of the properties that much more complex animals have, yet they don't have a single neuron inside them. They're just one cell. So we have to ask, how is the learning? Where is the reward function inside a cell like that? I believe it's in a quantum layer that's running inside the cell. So could harnessing a built-in reward function that's in the universe give reinforcement learning a boost? What we would hope to see, if this were the case, is that we take our standard classical reinforcement learning algorithm, which maximizes reward, learns to maximize reward over time, and we turn on the quantum part, and now it learns to maximize reward faster because it's using these built-in instincts, built-in functions. We can start running these experiments now. So as a scientist, this is the most exciting part of this whole research. And I want to show you an example of an experiment of this type. So this is a very simple robot. We're starting with very simple systems. And you can see that it's looking at different positions on this numbered grid. What we're actually doing with the robot here is we have its webcam data is coming in. It has a vision system that's being sent off to a quantum computer running remotely, and it's actually being used to shape this quantum wave function. And then that is being collapsed, and the collapse selects an action for the robot to take. So where the robot looks on the next time step is decided by the quantum system. So there's no reward function here. And what we expect to see, if the hypothesis is correct, is that when it's making decisions under control of the classical computer, they'll just be totally random. But when it's under control of the quantum computer, we might see a slight bias towards some actions being chosen more than others, which could reveal this built-in reward function. So it's early days, but this is a really exciting area of research. Because if we can understand conscious decision-making, this second mode of operation that AI is completely ignoring for now, I think we'll be able to finally enable AI in the physical world. Thank you.